start talking about the ideal gas law. We've already talked about Boyle's and Gay-Lussac and the combined gas law and Charles' law. So, but what happens if I now want to talk about moles? So remember in those properties we said that the moles were being held constant, and remember that moles are talking about a set of 6.02 times 10 to the 23 particles. So when we talk about moles, we're really talking about the number of particles. So it makes sense that all of these gas properties would be related to how many particles I have. If I have more particles, I need more space. I might have more pressure because I have more collisions. The movement of them is going to be mattering. So this is where we come up with a new law, the ideal gas law, which says that the pressure times the temperature, the pressure times the volume is equal to the number of moles times R, which is a gas constant, times the temperature in Kelvin. So the R, and there are various different values, but the one we're going to be using in our course that works well with the units for pressure and volume and temperature is 0.082057 liter atmospheres per mole Kelvin. Typically we use 0.0821, sometimes it's 0.08206, depending on how much precision we need in the calculations, but often it's 0.0821 is the value that we'll use. We'll round it off to the fourth decimal place. And then the units are quite important because these units help remind me that the pressure has to be in atmospheres if I'm going to use this value of R. The volume has to be in liters and the temperature has to be in Kelvin. So it's kind of a reminder. Many times we'll be seeing ideal gas law problems where I know I have to use the ideal gas law, but I may need to do some conversions of pressure or volume or temperature before I can apply it. So I'm just kind of reminding you that there's really just one law, the ideal gas law, and all these other laws we talked about are just special conditions. So if I have PV equals nRT, if the number of moles is constant, N is constant, then I end up with PV over T is equal to a constant because both N is a constant now and so is R, so it's just a bigger constant, we'll call it K, and I end up with the combined gas law. If in addition to N being constant, volume is constant, also the volumes are going to cancel out and I'm going to get Gay-Lussac. If it's moles and pressure, I get Charles's law. If moles and temperature are constant, I get Boyle's gas law. If we understand how we can kind of relate to these things, I basically just have to remember one gas law, and that's the ideal gas law. So here would be some samples that we're going to try in class. It's really a matter of making sure we understand we have the right units, we pick the right property for the right unit, and we make sure it's for the right variable. So in other words, we know that when I see liters, that's a volume property. So 2.3 liters is my volume. 32 degrees Celsius, well, that's my temperature, but it will need to be converted to Kelvin. 4.7 atmospheres is my pressure. So I have everything. I need to get my R value, and I'm going to set up my equation, rearrange it to solve for number of moles, and plug in my values and solve for it. So we'll do that problem in class. Just kind of point out, many of you have seen this in high school chemistry before, that we kind of have an ideal gas shortcut. I can calculate how much volume 1 mole of gas takes up at standard temperature of 273 Kelvin and standard pressure of 1 atmosphere. And it turns out that the volume of 1 mole at STP is 22.4 liters. So that means 22.4 liters equals 1 mole at those conditions. In that case, if I want to know how many moles I have, and I know I have 48 liters of gas, I just divide 48 liters by 22.4 and I can quickly get to moles. So it's a nice shortcut. Just be very clear. Many times we're not working at STP. Many times we're working at slightly different temperatures or pressures, and so the answer will be a little bit off. Now note that if standard temperature is 273 Kelvin and I'm working at room temperature 298 Kelvin, or the pressure is slightly off, it's 0.997 atmospheres. So if it's pretty close to 1 and pretty close to 273 Kelvin, I'm guessing my answer is going to be, my volume is going to be nearly 22 liters per mole, but it might be a little bit off. So, but sometimes that can help with estimating an answer and doing a check on, did I get the right answer? Does it seem reasonable?